All right, here we are for part D, chapter 1, Stoiching like a champ. This is a pretty big section, so it's going to be a little bit longer than usual, but lots of information. All right, so stoichiometry comes from a balance equation. A balance equation is just a recipe that you are having with a reactants, compounds, and elements, and you're making new compounds and elements. And the stoichiometry aspect of it is basically finding the mass of what you need and what you want to get. So it's a balancing of masses. So first thing is always to balance the equation. So you should get 1 Fe2O3, 3 COs, 2 irons, and 3 CO2s. Okay, here is our balance equation. So what do these coefficients actually tell you in the reaction? They're ratios. That means I need 1 part of iron oxide for 3 parts of CO. And that's what stoichiometry is, basically just showing ratios between moles of reactants and moles of products. Now, moles are easier used, and then we can convert that into mass using molar mass. So we use the stoichiometry of the chemical equation to calculate the mass of the reactants that we want and how much we actually make. So there's no waste. We can't just throw things in willy-nilly because we want to make sure the reaction occurs perfectly. Or we can use the stoichiometry to calculate the mass of the products that we wish to attain. This is more useful in experimental sciences because you can figure out actually what your yield is, what you should get, and what you get in the experiment, and how well your lab went. So what is the mole ratio between iron oxide and CO? And you look at the coefficients in front, and it says it's a 1:3 ratio. 1 mole of Fe2O3 for every 3 moles of CO. So a ratio is also a conversion factor. So we'll get to that. What is the mole ratio between Fe2O3 and CO2? Again, same value. It's a 1:3 ratio. And again, if it's a ratio, it's a conversion factor. That means you can convert 1 mole of something to another mole of something else. So you're going into dimensional analysis. And that's what stoichiometry basically is using, is dimensional analysis of chemistry units like moles and grams. All right, so ratio of the moles of reactants and product is used in DA to convert moles of one compound or into another compound. So here's some type of problems that you will see in stoichiometry. You have moles to moles, so that's just the mole ratio. You have moles to mass, so that's the mole ratio with the molar mass of something else. And you also have mass to mass, that has everything into it. You have molar mass, moles to moles, and molar mass. So you can see we're using molar mass or the mole to mole ratio in the balance equation. Volume. When you're dealing with volume, you're usually going to use gas or concentration, so either a gas or a liquid. In most cases, it's going to be volume, usually in milliliters, but yeah, make sure you convert to liters and then to moles using the concentration. So here's some problems with gas, the volume. Again, it can just be moles to moles, or to find volume, you're going to use the molarity, or if you're given volume, you have to use the molarity of A to find B. All right, so let's do some examples, moles A to moles B. So how many moles of Fe is produced from 2.34 moles of carbon monoxide? So your given information is 2.34 moles of CO. Draw your T-chart. We need moles of CO on the bottom, and there's 3 of them because there's a number 3 in front of CO. And there's 2 moles of Fe. Moles cancel out, zap zap, and you do your math, you get 1.56 moles of Fe. So you can see it's just a dimensional analysis problem using the coefficients. The coefficients are conversion factors. All right, let's find the mass of B from 2.34 moles of carbon monoxide. So from the previous problem, we got to this point, and we want to find the mass of Fe. So anytime you have mass, or looking for mass, you have to use molar mass. So the molar mass of iron is 55.845 grams. Moles are on the bottom because moles need to cancel, and you get 87.1 grams of Fe. That's a lot easier number. Well, that's a number that we can work with. We can't work with 1.84 because we don't know how much that, we don't have a scale of moles. We have to use the scale in grams. All right, the biggie, mass of A to moles of A to moles of B to mass of B. So mass is going to be molar mass. Moles is going to be the coefficient. So we have 45.6 grams of CO. We want to know how much iron is going to be produced. So our given is 45.6. You have grams. The only thing that converts grams and moles is molar mass. So the molar mass of CO is 28, and that's 1 mole of CO. Grams get canceled, zap zap. So now we have moles of CO on the top, the moles of CO on the bottom. It's 3 of them. 2 moles of Fe goes on top. Moles cancel, zap zap. And we need to find the mass. So again, we go back to molar mass of Fe, which is 55.8 grams of Fe. And moles go bye-bye. So you can see the dimensional analysis is different 4 steps, but they're always going to be the same. It's either molar mass or it's going to be the coefficients. And you get 60.6 grams of Fe. Alright, here's one with volume. So you're probably going to use the molarity. So how many moles of CO2 is produced from 50 milliliters of a 0.1 molar solution of iron oxide? So you're given 2 pieces of information. You're given the milliliters and you're also given molarity. Now remember, molarity is moles per liter or moles per decimeter cubed. That means it's a conversion factor. It's a derived unit. You're not going to use a derived unit in your given. So you're going to start with 50 milliliters of iron oxide. So we want to make sure we get that into liters. So 1 liter is 1,000 milliliters. Milliliters go bye-bye. Okay. So then we need liters on the bottom. And looking at the molarity, for every 1 liter, there's 0.1 moles of Fe2O3. Okay, that's the concentration. Liters go zap zap. And we want to find moles of CO2. 1 mole of Fe2O3 in the balance equation goes to 3 moles of CO2, and moles go bye-bye. Again, it's all dimensional analysis using your conversion factors that are given to you in the problem. The balance equation is a conversion factor, and the molarity is a conversion factor. And we get 0.0150 moles of CO2. So just review Stoich rules, write the chemical equation, make sure you balance the chemical equation, set up dA from given information, and you rock the Stoich out with your hands up in the air and wave them like you just don't care. Alright, here's some practice problems. So how many grams of KCl is produced if 6.89 grams of ClO3 are decomposed? Okay, so this is a mass to mole to mole to mass problem. It's a biggie. It should have 4 steps. Okay, so you should probably pause this, work it out, and see if you get the answer. Alright, we're going to start with 6.89 grams KCl3. The molar mass of KCl3 is 122.55 from the periodic table, and that's 1 mole of KCl3. So we're going grams to moles. Then we need to get 2 moles of KCl. So it's a 2-to-2 ratio or 1-to-1 ratio from the balance equation. So far we used the molar mass, the balance equation, Moles go zap zap. And then we have to get the moles. So again, you're going to grams. And then you're going to get 2 molar mass of KCl. Moles cancel. Do your math. You should get 4.19 grams of KCl. Alright, mass percent, pretty easy. It's just how much of a element is in the compound total in percent form. So you gotta make sure you multiply by 100. So in ethanol, you have C2H5OH. So there's 2 carbons, so a total of 24 O2 grams. There's 6 hydrogens, so about 6 grams. And there's only 1 oxygen, about 16 grams. So the total molar mass is 46.07 grams per mole. So percent of each element basically is how much carbon percent-wise, how much hydrogen, how much oxygen are in 46 grams. So for carbon, you take the total amount of carbon, 24, divided by the total mass, 46, 8 times 100, and you get 52% of carbon. So for hydrogen, same thing. Total amount of hydrogen is 6 grams over the total mass, 46, times 100, and you get 13.13 percent. And then oxygen, same thing. You take the amount of oxygen, this is about 16 grams over the total, and you get times 100, and you get 34% oxygen. So when you add those 3 numbers up, you should always get 100%. Alright, so time for practice problems. You want to find the percent of each element in copper sulfate, CuSO4, and find the percent of each element in C2H2, which is acetylene gas or ethylene gas. So for copper, sulfur, and oxygen, the total molar mass is about 159 grams. So for copper, you should get 39.81, sulfur 20%, and oxygen 40%. So for number 2, there's 2 hydrogens and 2 carbons, a total molar mass of 26 grams. So the percent of hydrogen is going to be pretty low, 2 over 26, 7%, and then carbon is 92%. Alright, last Stoich empirical molecular formula. So empirical is the smallest ratio of a compound, and molecular is the actual ratio of the compound. Oh, well, sorry, actual formula of the compound. The ratio is the same as the empirical. So empirical formula, water is the lowest common multiple, but also H2O is a molecule, so it's a molecular formula. Hydrogen peroxide is H2O2. If you reduce that, you get HO, which is not a formula, so it's empirical. SO2 is an actual compound, but it's also reduced, so it is both empirical and molecular. Butane, C4H10, is a molecular formula, but its empirical is reduced down to C2H5, which is not a compound. So here's checkup number 8. Hydrazine, if you write the empirical, you reduce it down to NH2. Octane would be C4H9. Benzene is CH, and then ammonia is already empirical, so it's still NH3. So how do you find the empirical formula? Again, it goes down to moles. So you want to make sure you have the moles of each element, so you need to make sure you convert grams to moles, and then you just do the ratio between large over small. So we have sulfur and oxygen, 25 grams of each, so you have to make sure you convert the 25 grams into moles. So 25 divided by 32, we get 0.78 moles of sulfur. Do the same thing for oxygen, 25 divided by 16, and we get 1.56 moles of oxygen. So you can see the largest one is oxygen, so you do large over small, so oxygen over sulfur, and when you divide, you get a ratio of 2 to 1. So that means there's 2 oxygens and 1 sulfur, So the formula would be SO2. Here's worked out example number 7 on page 9. So burning magnesium makes a bright white light, and you make magnesium oxide. So we have 0.46 grams of magnesium and 0.806 grams of magnesium oxide. Calculate the empirical formula for magnesium oxide. So we want the simplest ratio of magnesium and oxygen react according to the given data. So ultimately, we need the ratio between Mg and O. So what do we need to find first between Mg and O2? We gotta find out how much oxygen actually reacted. So subtract the 2, you get about 0.320 grams of oxygen. So now we know the masses Mg and O. We can do the next step to find the ratio. So we need the molar mass of both Mg and O. Okay, and then divide the numbers by the smallest value. So when you do that, you should get a ratio of 1 to 1, and that means the formula is MgO. Alright, example 2. We have an unknown copper compound between sulfur and oxygen, 40% sulfur, 60% oxygen. Whoa, we got a math alert. You gotta treat the percent just like grams. It doesn't matter how much sample you have. If it's in percent, make it grams. It doesn't matter if you have 1,000,000 grams or 100 grams, it's always going to be the same percent. So we treat 40% as 40 grams of sulfur, divided by 32, 1.25, and 60 grams of oxygen, divided by 16, and we get 3.75. So you can know that oxygen is larger than sulfur, so you do O over S, and it should come out to be 3 to 1 ratio, and that means the formula is SO3. Alright, you also have this worked out example on page 9 in your text, but you should try to do it. You want to find the empirical formula of this hydrocarbon between carbon and hydrogen, 85.7% carbon and 14.3% hydrogen. Again, treat the percent just like grams. So just take out the percent and put G there to find the moles of carbon and hydrogen. Okay. Alright, so how do we find the molecular formula from the empirical? So in most cases, the empirical is the lowest reduced formula, and sometimes the molecular is the empirical, but basically it's a ratio. So for example, we have 4 cheese cracker sandwiches. That means it consists of 8 crackers and 4 cheese middles. The empirical of that would be 2 crackers and 1 cheese middle. So the ratio is reduced down by 4. That means the molar mass will be reduced by 4. So if you have the empirical molar mass of, let's say, 5 grams, that means the molecular molar mass would be 20, because it's 4 times greater, 20 to 5, or even 4 times lower between 5 and 20. So it's a ratio again. So basically you're figuring out what the ratio between the molar masses are, and that's how much you need to multiply the empirical by. So for, again, if the molar mass of 1 cheese cracker is 5 and you have 4 of them, 4 times 5 gives you 20. So here we have, find the molar mass of the empirical from the periodic table using the molar mass to find moles in the mole ratio. Okay, do the molar masses between the molecular and the empirical, large over small. Sometimes they're the same because the molecular can be the empirical. Okay, so we have an empirical formula of SO2. The molar mass of its compound is 128. What's the molecular formula? So you basically have to figure out how many SO2s are there to make up 128. So one SO2 has a mass of 64. So in your head, you should be able to see, okay, well, that's basically twice as much, and you are correct. If you do 128 over 64, it's 2 to 1. That means the molecular is twice as big, so you need two SO2s, so S2O4 would be the molecular formula. You can see that being reduced can get SO2. Alright, so we have a hydrocarbon, 26 grams per mole. It contains 1.58 grams of hydrogen and 22.15 grams of carbon. What's the empirical and molecular formulas? So we have to find the empirical first. So we do hydrogen. 1.85 divided by 1 gives us 1.84 moles of H. And then 22.15 grams of carbon divided by 12 gives us 1.84 moles of carbon. So it's the same value. So the ratio is a 1-to-1 ratio. So the empirical is CH. Okay. So from the empirical, we can get the molar mass to be 13 grams. Again, you can see, simple math, that 13 times 2 gives us 26. So the ratio between 26 and 13 is 2 to 1. So we need twice as much CH. So the formula would be C2H2. All right, so quick review. Again, to find the empirical, you gotta use the molar mass of the empirical from the periodic table. The ratio between the molecular and the empirical, large over small, we'll see how much more times the molecular compared to the empirical. So we have 25 grams of each sulfur and oxygen, and the molar mass of that compound is 128. So again, you want to find the empirical to be SO2. We did this problem previously, finding the moles of each sulfur and oxygen. And the molar mass of SO2 is 64. So again, kind of thinking twice as much. So the ratio is 2 to 1. So that means the molecular formula would be S2O4. So you need twice as much SO2. All right, so this is a little long, 20 some minutes. So if you have any questions, let me know, and we can go cover that in class.